Hi, my name is Jennifer. In today's lab, we are going to discuss the ways in which we can use observational data to obtain an unknown. In this case, we'll be estimating the mass of a black hole by analyzing the positions of a nearby star over time. First, we need to review the physics principles which we will apply to the lab in order to obtain results. We will start by defining the system, which is the star in orbit, since it is the object we are interested in observing over time. Therefore, everything else, including the black hole and the rest of space, are defined as the surroundings. Next, we need to discuss the causes of motion on the system. The star is orbiting the black hole like so. In this situation, it is given that we can assume that gravity from the black hole is the only force acting on the star. The circular motion of the system's orbit calls for some additional explanation about the gravitational force. The gravitational force is split into two components due to the circular path of the system. The force parallel to the momentum, or the direction of the motion in this case, and the force perpendicular to the momentum. The parallel component of force always lies tangent to the curved path, and it dictates the speed of the orbit. The perpendicular component of force dictates the direction of motion. Therefore, we can extrapolate that it points toward the center of the black hole, which the star is orbiting. The summation of the parallel and perpendicular forces gives the total force. Knowing the magnitude of the force, we can calculate the mass of the black hole by rearranging the equation for gravitational force. It is worth noting that because the star orbits the black hole in an elliptical path, the distance between the star and the black hole is not constant, so the result of this calculation will give a different mass for each point. Still, the masses are relatively similar, and we can average the entire list to gain our best estimate. Even when setting the time between data points as large as 1 day, there are still hundreds of calculations to perform. Therefore, the most efficient ways to make these calculations is using a computer. We are using the GlowScript IDE in Python to do our calculations, as well as to generate a model of the star's motion. The first section of code takes in a seed, which randomizes the trajectory of the star. The next section of code establishes the visualization for the model and sets initial values for the calculations, including the gravitational constant, the mass of the star, and the time intervals between position data points. The mass of the star and delta t are 2 times 10 to the 30th and 1 day in seconds respectively, as specified in the assignment instructions. The x and y components of velocity are then calculated over time using the positions from the randomized trajectory and the delta t given. Forces on the system are calculated in a loop for every position. Using the initial and final velocities derived in the previous step, the change in velocity is calculated. The change in momentum can also be found, since momentum equals mass times velocity, and the mass of the star is known. We can estimate dp dt as delta p over delta t, since the time between data points is relatively small. Newton's second law defines dp dt as net force, so that is clarified here as well. The unitary vector of momentum is derived, as well as the momentum's change in magnitude. Multiplying these values together gives us the parallel component of force. As previously mentioned, the net force is the sum of the parallel and perpendicular forces, so we know that the perpendicular force must be the difference between the total force and the parallel force. Finally, we can apply the rearranged gravitational force equation in the loop. The radius is simply defined as the magnitude of the star's position, since the black hole is at position 0, 0, 0. The estimated mass of the black hole for each data point is then printed, as well as the magnitude of the net force and its components. We then use the aforementioned method of averaging all these data points together to estimate the mass of the black hole as 1.12 times 10 to the 34th kilograms. So, we know the mass of the black hole, but what are its implications? Well, the gravitational interactions between the star and the black hole cause the orbit, as the larger mass of the black hole pulls the star inward. However, the star clearly does not follow a straight path directly toward the black hole. This is due to the initial velocity of the star, which, when acted upon by the perpendicular component of gravity, experiences a change in direction and thus a force. The force in this direction is the parallel force. Now, what if the black hole was replaced by a different black hole, but the star's motion was unchanged? Since the gravitational force is the only force acting on the system, the mass of the new black hole must be the same as the previous one. The only factors that could change the net force and thereby the motion include the mass of the star, the mass of the black hole, and the distance between the two. Since the mass of the star is constant and the radius of the orbit remains unchanged, you could assume the new black hole is of the same mass. In previous labs, we have seen how we can predict motion. However, we have now used observational data to find unknowns that occurred in the past. Being able to look back in time as well as forward provides us with methods to use physics principles to analyze a system over any period of time. Thank you for watching. My code is in the description if you wish to explore further.